Let's look at second order time-independent perturbation theory, and we'll do a nice example of that as well. So this is what the equation looks like to second order, and what we want to do is apply psi n 0 star, essentially, on the left-hand side of each expression. So if we do that, we're going to get the following. That is the unperturbed wave function on the left-hand side. Now the assumption is that H0 is Hermitian, and therefore what we expect is that psi n0, H0 applied to psi n0, is equal to H psi n0 psi n2, or E n0 psi n0 psi n2. That means the first term on the left cancels the first term on the right. And of course, psi n0 psi n0 is equal to 1 since they're normalized. Therefore, we get E sub n2 is equal to psi n0 psi 1 psi n1. Minus En1 psi n0 psi n1, which of course is just 0. So this is the only term that survives, and I can write then En2 as sum over m and n. M, let's say, n not equal to n, Cm n psi n0 h1 psi m0, which is equal to sum m not equal to n psi m0 h1 psi n0 psi n0 h1 psi m0. Put it all together, we get this final expression, En, second order, m unequal to n, psi m0 h1 psi n0 squared divided by En0 minus En0. So this is my energy correction to second order, and this is the fundamental result of second order perturbation theory. Great. Let's put it into practice. Let's see if we can solve an interesting problem. Let's consider that we have a charged particle in a harmonic oscillator potential. Okay, we've done that before. Let's turn on a weak electric field and perturb the initial potential that way. Usually we talk about putting a charged particle like this in a weak electric field as a Stark effect. So first off, when we do this, let's show that when I turn on this weak field, there is no first order change in the energy, so I have to calculate the second order correction. So in this case, my perturbing Hamiltonian is minus Q times some electric field, script E, times X. Well, to first order, I can write this as psi n0 h1 psi n0, which will be minus Q times script E n x n. Those are my harmonic oscillator wave functions. The trick we're going to use is to write my two operators, a plus, a minus, as 2 over the square root of 2m times im omega x, such that x is equal to minus I over square root 2m omega a plus minus a minus, right? Raising and lowering operator. That means that x is equal to minus I over 2m square root times omega integral psi n star a plus minus a minus psi n dx. All right? But when those guys operate, a plus operating on psi gives me n plus 1 h bar omega psi sub n. A minus operating on psi gives me n h bar omega operating on psi n. And this is, sorry, psi n plus 1, psi n minus 1. That means that x, expectation value of x, is minus I over square root 2m omega n plus 1 h bar omega times the integral psi n star psi n plus 1 dx minus square root n h bar omega integral psi n star psi n minus 1 dx. Well, we can stop right there for the first order because notice, the eigenfunctions are orthogonal, therefore this is going to give me 0. Same thing here. So the entire expectation value has to be 0. And so to first order, there is no first order energy, a shift in energy levels. So we have to go to second order. All right, let's do that. Our equation for second order, E sub n squared is Q times E squared sum m not equal to n m x n over n minus m h bar omega. Right? Those are my squares and square energy difference in the denominator. Some algebra, we get QE quantity squared h bar over m h bar omega times 2m omega, sum m not equal to n, square root n plus 1, Kronecker delta n, n plus 1, minus square root of n, Kronecker delta n, and minus 1. All divided by n minus m. That gives me QE squared over 2m omega squared, m not equal to n, n plus 1 delta m n minus 1 divided by n minus m, which I can write as QE squared, QE squared, 2m omega squared, n plus 1, n minus n plus 1, which is just minus QE quantity squared divided by 2m omega squared. Nice. So that's going to be my second order correction to the energy. Well, let's just see how good this is. Let's solve the Schrödinger equation directly. We can do this by changing variables. Suppose we let x prime be equal to x minus QE over m omega squared. And solve, let's find the exact energies, and we can show that they're consistent with what we get with perturbation theory. So, Schrödinger equation, minus h bar squared, second derivative with respect to x, plus, and here's my potential, m omega squared x squared over 2 minus q dx psi equals e psi. But I can write this 1/2 m omega squared x squared minus q ex. I can write as 1/2 m omega squared x prime plus QE over m omega squared minus QE x squared plus QE over m omega squared. So this is equal to 1/2 m omega squared x squared, x prime squared, sorry, plus m omega squared x prime squared times QE over m omega squared plus 1/2 m omega squared QE squared over m squared omega to the 4th. Wow. Put all that together, my Schrödinger equation becomes minus h bar squared over 2m, second derivative of psi with respect to x, plus 1/2 m omega squared x prime squared psi is equal to, bring the stuff to the right, e plus 1/2 QE quantity squared over m omega squared times psi. So notice what happens. What we've done is we've made this shift that looks exactly the same. E sub n then, E sub n is just going to be equal to n plus 1/2 h bar omega minus 1/2 QE quantity squared divided by m omega squared. So it shifts by this much, just as the same answers we got from perturbation theory. So it's really nice. The second order answer that we get in perturbation theory is exactly the same as just making a change in variables in the Schrodinger equation and solving exactly. Really, really nice. Really nice example of a good use for second order perturbation theory. Sometimes we're not so lucky. So that was second order perturbation theory. But sometimes we have to resort to a method called degenerate perturbation theory. That's if you have, as you remember from the second order equation, you have two energies in the denominator. If those two energies are the same and one subtracts the other, you have a problem. You're dividing by 0. So this is what happens. If I have two or more distinct states that share the same energy, let's call them psi A naught and psi B. Suppose they both have the same energy eigenvalues. Ordinary perturbation theory is going to fail. This is what we call a degenerate case. So what we have to do is use degenerate perturbation theory. So let's suppose my unperturbed Hamiltonian applied to psi A gives me E naught psi A. Same unperturbed Hamiltonian applied to psi B gives me also E naught psi B. And of course, assumption being that the eigenfunctions are orthogonal. So any linear combination of psi A and psi B will still be a solution, still be an eigenstate of H naught with eigenvalue E naught. So we can write, for example, H naught psi naught equals E naught psi naught, where psi naught is just some linear combination alpha psi A plus beta psi B. The perturbation in this case will lift the degeneracy. So as lambda increases from 0 to 1, the unperturbed energy then is going to split into 2. If we turn off the perturbation, the upper state reduces down to one linear combination of psi A and psi B again. Lower state reduces to some orthogonal linear combination. So we have to figure out how we can constitute good linear combinations. We're going to solve H psi equals E psi, where H is going to be H0 plus lambda H1. And E is going to be E0 plus lambda E1 plus lambda squared E2, and on and on. And psi will be equal to psi 0 plus lambda psi 1 plus lambda squared psi 2, correction, and so on. So if we insert these representations into H psi equals E psi, and then equate like powers of lambda, kind of as we did before, we'll get the following. H0 psi 0 plus lambda H1 psi 0 plus H0 psi 1 0 plus lambda E1 psi 0 plus E0 psi 1. We can write this as H naught psi naught equals E naught psi naught H naught psi 1 plus H1 psi naught equals E naught psi 1 plus E1 psi naught. Let's take the inner product with psi A0. So if we do that, we get psi A0, H naught psi 1 plus psi A0, H1 psi naught equals E naught psi A0 psi 1 plus E1 psi A0 psi 0. Now, since H naught is Hermitian, the first term on the left-hand side should cancel the first term on the right-hand side. And remember, we had said that psi 0, we're going to write it as alpha psi A plus beta psi B 0, 0. Put all that together, and we have alpha psi A 0 H1 psi A 0 plus beta psi A 0 H1 psi B0 is equal to alpha E1 or we can rewrite this a little more simply as alpha W A plus beta W B A B is equal to alpha E1, where Wij generic is defined as psi I0 H1 psi J0. And of course, in our case, I and J are just going to represent A and B. Also, the inner product with psi B0 gives us alpha WBA plus beta WBB equals beta E1. So the W's are matrix elements of the perturbation with respect to the unperturbed wave functions psi A and psi B. And so we'll put it together, we get alpha WAB WBA minus E1 minus WAA E1 minus WBB equals 0. Now, since WBA equals WAB star, we can write a fundamental result in degenerate perturbation theory. E plus minus 1, first order correction is 1/2 WAA plus WAB plus or minus the square root WAA minus WBB squared plus 4 WAB squared. The roots correspond to two perturbation or perturbed energies. So, this is the fundamental result of degenerate perturbation theory. Now, this looks like a lot of work, and sometimes there are going to be easier ways to solve this. We'll do this next time with an example using the degenerate example for a three-dimensional cubical well.